Dear students, welcome to Tungal online classes. In previous class, we have completed the numerical problems of electric charges and electric fields. In today's session, we shall start with the next chapter, that is electrostatic potential and capacitance. Okay, the concepts we are covering in today's class are introduction to electric potential, then electrostatic potential energy, then we have electrostatic potential, then there is derivation of potential due to point charge, and we have to derive the relation between electric field and electric potential. Okay. So, in first year classes, in the chapter of work, power, energy and gravitation, we have come across the term potential energy. Yes, do you remember that? See here, if I have any object, I am holding in my hand here. So, if I throw this chalk piece vertically upwards, yes. So, for throwing this chalk piece vertically upwards against the gravitational force of the earth, I have to apply some external force. This chalk piece does not move by itself, is it not? So, if this is the object, always there is gravitational force acting on any object on the surface of the earth. That gravitational force is nothing but weight of the object, that is given by W is equal to m into g. Okay. If I have to move this object against this gravitational force, I have to apply the force vertically upwards, right? So, that external force must be equal to what? So, that must be weight of the equal to weight of the object. Okay. So, let us say I am applying some external force like this. So, because of this external force, let us assume the object is displaced from position A to B. Okay. A is the initial position of the object, B is final position of the object, and let us consider the displacement of the object between positions A and B. Let it be h. Okay. H is the displacement between positions A and B. Okay. So, whenever there is force acting on the object and there is a displacement of the object, look at this. On this object, we are applying the force of F external here, and because of this external force F, and there is a displacement of the object between positions A and B, and we know whenever there is force acting on an object and there is displacement caused, so we say work is done. Okay. So, that work done is given by what? Work done is equal to the force applied into displacement of the object. Okay. So, here by applying the force and moving this object by the height of h, we are doing some work here. Okay. And whatever work is done on this object between positions A and B, so that work done gets stored in this object in the form of potential energy. Okay. So, that potential energy is given by m into g into h, because F external is equal to what? M into g, that is external force applied is equal to weight of the object. Okay. So, this potential energy stored in the object at the maximum position, so that potential energy is called the gravitational potential energy. Here we are doing the work against the direction of gravitational force, hence this potential energy we refer it as the gravitational potential energy. And when this force is removed here at position B, at the highest position B, the velocity will be equal to 0. Yes. So, whatever potential energy is stored, so at this point, from this point, the object starts falling down again. Okay. And so, it will use the same potential energy stored. So, at this position, it is having maximum potential energy, which is equal to m into g into h. After reaching the maximum height, the object starts falling down again, and to fall down from position B to A, this object will use the same energy which is stored in the form of gravitational potential energy. Okay. And when it reaches from B to A, it will lose all the energy stored in the form of potential energy. Okay. That is why during this motion, the net sum of the kinetic energy and potential energy remain conserved. So, such forces are called conservative forces. Okay. Similarly, if I consider another example of a spring, okay. So, we shall consider a spring like this. So, in the relaxed position, we have the spring like this. Yes. So, what we shall do? Let us apply some force here. I am applying some external force, and I am trying to compress this spring. Okay. So, let this spring be compressed by certain distance here. right? So because of the force applied, there is deflection of the spring, okay, and this compressed distance is how much? So let me call this is S, I call it is, okay. The deflection of the spring is what? S, and this deflection is caused by the external force applied, is it not? So here also I am doing some external work, and because of this external work there is some displacement of the object, that is deflection of the spring. So here also there is some work done. Work done is equal to what? The magnitude of the force applied and compression length of the spring. Yes, and whatever work is done on the spring, here the energy, whatever work is done, that work done gets stored in this spring here. So that is also potential energy. The work done on the spring gets stored in the spring in the form of potential energy, okay. And when this spring is released from this compressed state, this will bounce back again, okay. For that bouncing back, it will use the same energy stored in its compressed state, okay. It will have stored some energy which is equal to the work done on the spring. So that stored energy it will use and it will bounce back again, and it will move to the original position again. Okay, so these two are examples of conservative forces here. Okay. Similarly, when we consider the electrostatic force, we shall check whether that is conservative force and will there be any potential energy just similar to this gravitational potential energy and potential energy in the case of spring here. Now, let us consider the potential energy in the case of electrostatic force. Okay. So, for that what we shall do here is, let me consider a source charge. I will take it as a plus q here. For understanding, I am taking it as a positive charge, okay. And as we know, the positive charge always exerts the electric field outwards, okay. And let us consider this is a electric field which is along positive x direction we shall take here, okay. So what I will do here, let me consider a test charge along the path of this electric field. The test charge also we shall take it as a plus q here, okay. And that the test charge is placed at position A, yes. And as we know, the test charge experiences the repulsive force due to this source charge. So the direction of the electrostatic force will also be along a positive x direction away from the source charge, okay. So this is the direction of electrostatic repulsive force exerted on the positive test charge by the positive source charge here, okay. So to consider the concept of potential energy, so what we did in the gravitational force, in the case of gravitational potential energy, we have moved the object vertically upwards because the gravitational force was downward here. So we have moved the object vertically upwards in the opposite direction of gravitational force, okay. Similar to that, so here also what we shall do is, the electrostatic force is along positive x axis, but we shall move the charge in the opposite direction of electrostatic force. So I can move this charge from position A to, let us consider I am moving it up to position of B for a certain distance here, okay. So for moving this electric charge from A to B against the electrostatic force here, I have to apply some external force, okay. That external force must be minimum equal to the magnitude of the electrostatic force here, okay. So this external force I write it as F external. This F external must be equal to, this F external must be equal to what? Electrostatic force, and it is in the opposite direction here, okay. So here what is happening here, I am moving the charge against the direction of electrostatic force for certain distance from A to B, yes. And so whenever there is external force applied on any object and there is displacement of that object, there must be some work done here, okay. So here also I am doing the work against the electrostatic force. What is the magnitude of that work done? So for that what we shall do here, so let me consider very small distance here. So this is a very small distance, I call it as dr, okay. The work done in moving the charge, that is test charge plus q from A to, so let me call this is C here, A to C for the very small distance of dr. So that work will be equal to what? That I call it as a dw here, okay. So So that dW is given by the force applied is equal to what? So that is F external into what is the small displacement of the charge from A to C. So that I call it as a dr. Okay. So this is the small work done between A to C, but I am moving the charge actually from A to B here. Yes. So that work done to move the charge from A to B. So this can be given by integrating this small work done. So that is integration of dW between the limits of A to B. This is how we write the expression for the work done between the positions of A to B here. So this I can write it as WAB is equal to what? So that is integration of F external into dr between the limits of A to B. Okay. But we know F external is equal to what? Minus of F into E. So that can be written as WAB is equal to what? Integration between the limits A to B FE into minus of FE into dr. Okay. So this is the magnitude of work done in moving the charge from A to B against the electrostatic force. Okay. And whatever work is done in moving the charge from A to B, so that gets stored in the form of potential energy. Okay. So that work done gets stored in the charge in the form of potential energy. This potential energy stored in the charge, we call it as electrostatic potential energy. Okay. So for understanding here, I am taking the initial position of the charge as A and final position of the charge as B here. But conventionally what we do here is, so always we assume, yes, we assume the initial position of the charge is at infinity. We are free to assume the position of the charge here. See here, let us consider this is the source charge. Okay. Let it be at the origin here. Okay. And let us consider this is the electric field direction. Okay. And let us consider this is the point P within the electric field of this source charge. Okay. So the position of that A and B I can choose as per my convenience. So what we will do here is, initially I will consider the test charge. Test charge always we take it at infinity here. So why we are taking infinity? At that point this source charge does not have any influence. Okay. The electric potential at infinity will be equal to 0. That is the conventional way we consider the initial position of the test charge. Okay. So here the test charge is at x is equal to infinity. Okay. And I am moving the charge from x is equal to infinity to position P here. Okay. So whatever work is done, see here, let us assume the electric field is along a positive x direction. So I am moving the charge from infinity to given point within the electric field against the direction of electric field. Okay. So for this I have to apply some force here. So I am applying some force of F external, and that F external is equal to what? That is equal to negative of electrostatic force. Okay. So this work done to move the test charge from infinity to given point against the direction of electric field without any acceleration. Why I am considering without any acceleration? Because whatever force is applied, that is just exactly equal to the electrostatic force. Both are counterbalancing each other. So there is no acceleration of the charge. The charge is infinitesimally slowly moving from infinity to given position here. So we consider there is no acceleration of the charge. The external force applied is just equal to the electrostatic force of repulsion here. Okay. And whatever this work done is there, work done to move the test charge from infinity to given point against the direction of electric field without any acceleration, that work done is called the electrostatic potential energy. Okay. So it depends on which point you are taking here. If you consider this point P here, so it will be having some electric potential UP. If you consider another point R, so here there will be some electrostatic potential energy, that is UR, because as the distance increases you have to do more work. Okay, that too especially when you move towards the source charge here. As you move towards source charge, the repulsive force magnitude increases, hence you have to do more and more work here. So at different points here, every different point will have its own electrostatic potential energy. Okay, so point P has electrostatic potential energy of UP, point R has electrostatic potential of UR here. The electrostatic potential energy at P, how will you define it? It is the work done to move the test charge from infinity to given point P against the direction of electric field without any acceleration. Okay. Similarly, the potential energy at point R is defined as it is the work done to move the test positive charge from infinity to point R against the direction of electric field without any acceleration here. Okay. So, this is the electrostatic potential energy at point R. Okay. So, then we have electrostatic potential energy difference. Here what is this? Electrostatic potential energy difference. Okay. So, for this I have to consider 2 points P and R. Okay. So, at P the electrostatic potential energy is what? UP. At R the electrostatic potential energy is what? UR. Okay. The electrostatic potential energy between these two positions, so that I call it as UPR. UPR is the electrostatic potential energy between points P and R. So, that is given by the electrostatic potential energy at point R minus of the electrostatic potential energy at point P here, because in this case clearly you can see here UR is greater than UP, the potential energy at R is greater than the potential energy at point P, because point R is much away from infinity than point P. So, more work is done to move the charge from infinity to point R than the work done in moving the charge from infinity to point P here. Okay. The electrostatic potential energy difference between any 2 points in the electric field of a source charge is the work done to move the test charge from between these 2 positions without any acceleration against the direction of electric field. Okay. Here the electric field is along R to P and we are moving the charge from point P to point R against the direction of electric field. Okay. So, here the electrostatic potential energy at point P is equal to UP, the electrostatic potential energy of point R is equal to UR. Mathematically, this electrostatic potential energy difference is also given by UPR is equal to UR minus of UP. Okay. That is the basic definition of electrostatic potential energy difference between any 2 points. Next, let us discuss the concept of electrostatic potential. There is slight difference between electrostatic potential energy and electrostatic potential. See here. So, when we were considering the electrostatic potential energy at any point due to a source charge, see here, if this is point P here, the electrostatic potential energy at point P, it is the work done to move the test charge. So, I am taking the test charge from infinity, x is equal to infinity to given point P here. Okay. And it is the work is done against the direction of electric field. Electric field is along positive x direction, but the test charge is moved in the opposite direction of negative x direction here. Okay. The electrostatic force is along positive x direction, the external force is applied in the opposite direction of electrostatic force. Okay. And we have written the expression for that. W is equal to what? Integration of Fe into dr. Okay. So, this is the basic definition of work done. Okay. So, in this case see here, and this work done will be equal to what? So, that is equal to potential energy. Yes. So, this potential energy depends on the value of the work done. So, this work done depends on what is the magnitude of electrostatic force. Okay. And we know this electrostatic force is also given by charge into electric field intensity. Okay. So, where this q is magnitude of the charge which is moved against the direction of electric field, and this capital E, it is the electric field intensity of the source charge. Okay. Observe here. So, this electrostatic force depends on the magnitude of the test charge as well as it depends on magnitude of the electric field intensity of the source charge here. Okay. So, if q increases, if the magnitude of the test charge increases, the electrostatic force also increases. If the magnitude of the test charge decreases, the electrostatic force also decreases here. Okay. So, when this electrostatic force changes, the work done also changes. When the work done changes here, the potential energy, the electrostatic potential energy stored in the charge also changes. Okay. Hence, by observing all this, we can say that the electrostatic potential energy stored in the test charge, it depends on the magnitude of the test charge as well as the magnitude of the electric field intensity. So, it definitely depends on the magnitude of the test charge. But what we want here is, we do not want this dependency of the electrostatic potential energy on the magnitude of the test charge. Okay. So, we wish to consider this electrostatic potential energy to be the characteristic of the electric field. So, that is the property of the source charge. Okay. So, we want this electrostatic potential energy to be independent of the magnitude of the test charge. Okay. So, for that what we do here, so there are two ways. So, first one is what, either I will consider this test charge is equal to what, plus 1 coulomb I will take. Okay. So, if I take plus 1 coulomb charge, what happens, the electrostatic force will be equal to what, when this q is equal to 1, so I can write it as 1 into electric field. Okay. So, this value of q does not change the magnitude of the electrostatic force, hence this value of the q does not change the value of electrostatic potential energy. So, when I take the magnitude of the test charge as unit positive charge, that is equal to plus 1 coulomb, the electrostatic force just depends on the value of magnitude of the electric field intensity. So, in this case, when the test charge is 1 unit, if I take q is equal to plus 1 coulomb, purely the electrostatic potential energy, it is just the characteristic of the source charge here, that is the electric field intensity of the source charge. So, this is one way of doing this, or even if you have some charge of q here, what I will do here is, I will divide, if the work done is w, if the work done to move the charge from infinity to given point, total work done if it is w here, I will divide that w by q here, both are same. Okay. So, this parameter, that is total work done divided by the total magnitude of the test charge. So, that is again, it is independent of the test charge here. Okay. So, here this we call it as a electrostatic potential. Okay. So, electrostatic potential, in electrostatic potential energy, we were considering the magnitude of the work done to move the given quantity of the charge, from infinity to given point. But when I say electrostatic potential at any point, so in this case I have to consider the test charge as a unit positive charge, it cannot be q. So, I take the value of q is equal to what, plus 1 coulomb. Okay. That is the only difference between electrostatic potential energy and electrostatic potential. Okay. So, in electrostatic potential energy, we are considering the work done to move the given quantity of the charge from infinity to given point. But when I consider electrostatic potential, I will take the magnitude of the work done to move the unit positive charge from infinity to given point. Here just q is equal to plus 1 coulomb charge. Okay. If I replace the charge q, so here what happens, if I replace this test charge q by plus 1 coulomb charge, so that time electrostatic potential energy can be written as electrostatic potential at that point. Okay. So, let us define the electrostatic potential at any point in the electric field of a source charge. Okay. So, it is the work done, to move the unit positive charge, it is the work done to move the unit positive charge from infinity to given point, against the direction of electric field without any acceleration. Okay, so that is the basic definition of electric potential at any point. It is the work done to move the unit positive charge from infinity to given point against the direction of electric field without any acceleration. Okay, so that is the basic definition of electrostatic potential. Okay, so here also we have something called electrostatic potential difference. See here, if I have 2 points here, let me say this is P and this point is R. Okay, and the electrostatic potential at P, let me call this as Vp here. Okay, electrostatic potential energy is written by the symbol of U. So electrostatic potential will be written as the symbol of with the symbol of V here. Vp is electrostatic potential at P and Vr is electrostatic potential at point R. What is Vp here? It is the work done to move the unit positive charge from infinity to point P against electric field without any acceleration. Similarly, Vr, it is the work done to move the unit positive charge from infinity to point R against the electric field without any acceleration. Okay, so if I say the electrostatic potential difference between points P and R, it is the work done to move the unit positive charge from point P to point R against the direction of electric field without any acceleration. Okay, so here I am just considering these two positions. My initial point is P and the final point is R. Here I am moving the unit test positive charge from point P to point R against the direction of electrostatic field. Okay, so this is called the electrostatic potential difference between these two positions. Okay, and the work done to move the charge from P to R is given by the electrostatic potential difference, that is Vrp into the magnitude of the charge here. So that is Q I will take. Okay, next we have very important derivation of electrostatic potential due to a point charge. Okay, so this is a regularly asked question here. Carefully observe the derivation. Okay, so let us consider a point charge of magnitude plus Q I will take here. Okay, and let us consider this is the direction of electric field. Okay, along the path of the electric field, let me consider a point P here. Let me consider a point P at which I have to find out electric potential due to this source charge. Okay, and this point, let it be at the distance of R here. Okay, I am taking the electric field line along positive x-axis. Okay, then so by basic definition of electrostatic potential, it is the work done to move the unit positive charge from infinity to given point. Okay, so first we shall not take directly the infinity and given point. I will take two intermediate positions. Okay, so let me consider two positions here. So this is position A I will take and this is position B I will take. Okay, and let me take the unit positive charge Q is equal to +1 coulomb at point A here. Okay, and let us consider the distance of this test positive charge. So let it be at the distance of x from source charge. Okay, and let us take these 2 points A and B, let them be at very small distance of dx here. Okay, by considering these 2 points, I will form a mathematical equation. For that mathematical equation, I will apply the limits between infinity to given point. Okay, so that we shall see how to check it out, how to get it. Okay, and this is the point of infinity. Okay, and now let us consider the charge placed at point A here. Okay, since this is also positive charge, there will be repulsive force between this source charge and test charge. Hence, your electrostatic force, that is Fe, will be along a positive x direction. Okay, and what is the magnitude of this test charge? So this will be equal to what? Fe is equal to 1 divided by 4 pi epsilon naught. So which two charges I have to take? I have to take the source charge is what? Capital Q, and the test charge is what? Small q, divided by what is the distance between these two charges? That is x square here. Okay, and we know the magnitude of this test charge is equal to what? That is plus 1 coulomb here. So let me substitute that. So this implies the electrostatic force exerted on the test positive charge because of the source charge is given by, that is equal to 1 divided by 4 pi epsilon naught into capital Q divided by x square. Let this be equation number 1. Okay, but when I am considering the electrostatic potential, what we do here, I am moving this test positive charge in the opposite direction of electric field. So electric field is also in the same direction of electrostatic force here. Both are along positive x direction. But what I will do, I will move the charge against the direction of electrostatic force by applying the equal and opposite force. Okay, so I am applying F external along A to B, which is exactly opposite to the electrostatic force. Okay, and the magnitude of this external force must be equal to what? So that is equal to the magnitude of the electrostatic force acting on the test charge because of the source charge here. Okay, and let us consider I am moving this test charge from A to B. Yes, so what I am doing here, let us move this test charge, unit test positive charge, from position A to B for the distance of dx. Okay, so when I am moving this from position A to B for very small distance of dx, there is some work done. Okay, so that I write it here, work done in moving. So what is that? Work done in moving Q is equal to 1 coulomb charge from A to B, So let me write this as dw. dw is equal to what? So that is equal to the force applied. What is that? That is F external into what is the displacement of the object between A and B. So that is very small distance of dx. Okay, so that is equal to what? Dx I will write here. Okay, but we know this external force is equal and opposite to the electrostatic force. Hence I can write F external is equal to what? Minus of electrostatic force. So wherever I have F external here, I will replace this by minus of Fe. So this small work done between position A to B, so that is equal to what? Minus of Fe into dx. Okay, this is the magnitude of the work done in moving the charge from A to B. And let us substitute what is the value of Fe here. From equation number 1, I can write, so this small dw is equal to what? Minus of Fe is equal to what here? That is 1 by 4 pi epsilon naught capital Q divided by x square into dx. This negative sign is because it is in the opposite direction of electrostatic force. Okay, so this is the expression for small work done between A to B. Okay, this is general mathematical equation here. Okay, but by the definition of electrostatic potential, it is the work done to move the unit positive charge from infinity to given point. Okay, actually these points A and B, those are my intermediate positions, those are not the final positions. Okay, only to form this equation, I have considered these two intermediate positions. Yes, but for defining the electrostatic potential, the initial position of the test positive charge must be infinity, and the final position of the test positive charge must be equal to what? So that must be equal to point P here. Okay, so at point P I have x is equal to r, and here I have x is equal to infinity. So what I will do? I will consider the work done. I will consider the work done to move the charge from x is equal to infinity to x is equal to r. Okay, and that work done will be nothing but the electrostatic potential at point P. Correct? So what I will do here, the total work done, yes, total work done in moving Q is equal to plus 1 coulomb charge, Q is equal to plus 1 coulomb charge from infinity to point P, from infinity to point P. So this can be obtained by integrating this small work done between the limits of infinity to R. Okay, so that work done is given by W is equal to integration of dW, integration of such small work done between the limits x is equal to infinity to x is equal to R. X is equal to R is nothing but point P here. Okay, so let me substitute the equation of dW here. So W is equal to integration between the limits infinity to R. It is understood that these are the values of x here, so I simply write x to R. Yes, so dW is equal to what? Minus of 1 by 4 pi epsilon naught q divided by x square into dx. Observe this equation here, this minus 1 by 4 pi epsilon naught and q are common, you can take them outside. Only 1 by x square is the variable, only that I will remain inside the integration symbol here. So this I can write it as minus of 1 by 4 pi epsilon naught q integration between the limits of infinity to R. 1 by x square I can write it as x raised to 2, x raised to minus 2 into dx. Okay, so by integrating this I can get the total work done between infinity to position P here. Okay, and I know the equation for integration of x raised to n into dx, that is equal to what? X raised to n plus 1 whole divided by n plus 1 here. In case of n, I have, in this case in place of n I have minus 2 here. So by simplifying that I will get W is equal to what? Minus of 1 by 4 pi epsilon naught, q is constant here. So I will take it as x raised to minus 2 plus of 1 whole divided by minus 2 plus of 1, and I have to apply the limits here. Yes, so limits are what? Lower limit is infinity and upper limit is R here. Okay, and by simplifying this I will get it as minus of 1 by 4 pi epsilon naught q. Okay, so here I will have x raised to minus 2 plus of 1 is x raised to minus 1, okay, whole divided by, so this I can write it as x raised to minus 1 whole divided by minus 2 plus of 1 is minus 1. This minus get cancelled here, so I can write the work done is equal to what? That is equal to 1 divided by 4 pi epsilon naught into q. So this here I have to apply the limits between infinity to R. Okay, so this x raised to minus 1 can I write it as 1 by x. Okay, I'll write it as 1 by x between the limits of infinity to R. And how to apply the limits here? First I have to apply the upper limit in place of x, minus I have to apply the lower limit in place of x here. So this can be written as 1 by 4 pi epsilon naught q inside bracket. So first in place of x I will write it as 1 by R, that is upper limit minus of 1 divided by infinity. I know anything divided by infinity is equal to 0. So this I get it as W is equal to 1 divided by 4 pi epsilon naught q divided by R. This is 1 by R minus of 0, that I get it as 1 by R here. So this is the magnitude of the work done in moving the charge from infinity to given point at the distance of R. Okay, and by the definition of electrostatic potential, so this work done itself is the electrostatic potential at point P here. So by this I can write it as the electrostatic potential at point P is equal to what? 1 divided by 4 pi epsilon naught q divided by R, where q is the magnitude of the source charge and R is the distance of the point of consideration and the position of the source charge. Okay, so it is one of the easiest derivations that you can get it for 5 marks. Okay, I hope the derivation is clear. Neatly explain the initial considerations and you will get 5 out of 5 marks by writing it completely here. Next we have the relation between the electric field and electric potential. This is also regularly asked question for 3 marks. Okay, so for this let us consider a source charge here, so that I write it as plus q. Okay, and let us consider the direction of electric field along a positive x axis. Okay, so in this electric field path. So what I will do, let me consider a 2 points. Okay, so let this be point A and let this be point B here. Okay, at point A I will have a unity positive charge of Q is equal to plus 1 coulomb charge. Okay, and let us consider the electric potential at A, the electric potential at A, that I call it as see here. So we know the point which is closer to the source charge, it will have more electric potential, and the point which is away from the source charge will have some less magnitude of electric potential. So if the electric potential at B, if I write this as capital B here, at point A there will be electric potential lesser than this electric potential V. So that I write it as V minus of dV. Okay, so V is the electric potential at point B because of the source charge, and V minus dV is the electric potential at point A because of the source charge. Since it is little bit away from the point source charge, hence it is having lesser value of electric potential. Okay, and let us move this charge plus 1 coulomb from point A to point B. Okay, so for that, first let us consider what is the electrostatic force acting on the test positive charge because of the source charge. So that I write it as Fe. Okay, and this electrostatic force will be equal to what? 1 divided by 4 pi epsilon naught. So what are two charges here? Capital Q into small q divided by what is the distance between these two charges? So let this be r here. So this I write it as r square. Okay, but clearly Q is equal to what? Plus 1 coulomb charge. Substitute this, what you will get here? 1 by 4 pi epsilon naught capital Q into 1 divided by r square. And when the test charge, any one of the charges is equal to plus 1 coulomb charge, I can easily write the electrostatic force is equal to what? That is electric field intensity. So here I can write this electrostatic force is equal to what? So this is equal to electric field intensity at that point, because one of the charges is equal to what? Unity positive charge. Okay, so here instead of taking Fe, simply I take it as E here. Okay, so let this be equation number 1. Okay, and when I am moving the charge from point A to point B, I have to apply the force. I have to apply the force in the opposite direction of electric field. Okay, small work done, the small work done in moving the charge from A to B in the opposite direction of electric field is given by what? So that I write it as dW is equal to F external into what is the distance between these 2 points. So let me take it as dr. Dr is very small distance between A to B here. So I will write it as F external into dr. Okay, but F external is equal and opposite to electrostatic force. So I can write it as F external is equal to what? Minus of Fe. So this I can write it as dW is equal to minus of Fe into dr. Okay, but without taking Fe here, I can replace this Fe by what? dW is equal to minus of E into dr. Let this be equation number 2. This is the work done in moving the unit positive charge from point A to B. Okay, so this is first part of the derivation. Okay, and while understanding the electrostatic potential, see here, so this was our source charge here. So here I have 2 points. Okay, let me take this point as A, let me take this point as B here. If the electrostatic potential at B is equal to VB, if the electrostatic potential at A is equal to what? VA, the electrostatic potential difference between these 2 points, so that I call it as potential difference between these 2 points, it is the work done. What is that? This is the work done in moving the unit positive charge from A to B. Okay, so this is the work done in moving unit positive charge from A to B. So here I can write W is equal to what? The potential difference between these 2 points. So that I can call it as VBA. Okay, so this potential difference between these 2 points is nothing but the work done in moving the unit positive charge from A to B here. Okay, similarly consider this case here. Here also I am moving the unit positive charge from A to B. Okay, so whatever work is done, so that is nothing but dW is equal to what? Minus of E into dr. So this work done is nothing but the potential difference between positions A and B. Okay. So in this case, if I consider the potential difference between A and B, you are moving the charge from A to B. So your initial position is A and the final position is B. The potential difference will be equal to what? The potential of the final position minus of the potential of the initial position. So this I call it as VBA is equal to, it is nothing but the small work done. Small work done will be equal to what? The potential difference between those 2 points, VBA. So that is equal to what? VB minus of VA. Okay, but VB is equal to what? Here I have taken it as V minus of VA is equal to what? VA is equal to V minus of dV I will take. Okay, I simplify this, what will get here? So I will get it as this work done is equal to V get cancelled here, minus into minus, I will get it as a dV. Okay, so dW is equal to what? dV here. Let this be equation number 3. Equate equation number 2 and 3, both are same here. So by this I can write it as minus of E into dr is equal to what? dV. Okay, so from this I can write E is equal to minus of dV divided by dr. Okay, so this is the relation between electric field intensity and electrostatic potential. Okay, so electric field intensity is a negative gradient of electrostatic potential. Okay.